Hi, I am Corentin Dumry, a PhD student at EPFL in Switzerland, and today I'll be presenting Evocube, a genetic labeling framework for Polycube-Maps. So to begin with, polycubes are sets of axis-aligned cubes. And the important thing to notice here is that all face normals are aligned with the 6 principal axes, where you consider both direction of every axis. Our goal during this presentation will be to deform an arbitrary shape to a polycube. So apart from looking cool, polycubes are also used for quadrimeshing, but most importantly, they're used in hex remeshing, where the goal is to partition a 3D volume into hexahedra. Now, why do we care about hex meshes? So to perform finite element simulation, the first thing you'll need is a subdivision of the volume into elements. Subdividing a volume into tetrahedra is a well-studied problem and leads to meshes like this. Hexahedra, on the other hand, tend to lead to simpler structures, and in many cases are preferred by physicists as they're able to nicely follow the curves of the objects. In practice, finite element methods typically lead to the same results approximately, whether the mesh is hexahedra or tetrahedra, but with hexes the number of elements is usually much less, leading to reduced computation time as well as memory footprint, both of which can be a major issue in large simulations. So what does this have to do with polycubes? Well, imagine we have a nice polycube parameterization of the input shape, represented as a function f. In polycube space, subdividing the volume into a hexahedra is trivial. Then we can simply invert f and warp our hexes back into input space, using some previous work. But hex meshing using polycubes is just one of the 3 main families of hex meshing in literature. Another line of works subdivides the volume into an octree and runs an algorithm similar to marching cube. This is the only robust method, but it produces very low quality meshes. As you can see here, there are cells of different size and they're not aligned with the features. And overall, the mesh is quite complex. There's also a line of work using frame fields, which produces excellent meshes, but it's not robust at all and it will fail on any realistic input. Polycubes stand out as a nice middle ground that produces very good meshes and is still quite robust. When it comes to deforming an arbitrary shape to a polycube, we first need to precompute the polycube topology, here in blue, white, and red, and then we can deform the shape. And while this constrained shape deformation is a well-studied problem, precomputing polycube topology directly on the input mesh remains a challenge. So for a bit of context, polycubes were introduced in computer graphics by Tarini and colleagues, and were first used as a convenient approach to texturing. A few years later, Gregson and colleagues proposed a labeling method for polycubes, so that is to say, coloring the mesh in blue, white, and red, corresponding to each of the principal axes. Then their method was refined by Livesey and colleagues, who further used a graph cut segmentation approach to improve on their labelings. Now, our method. So coming back to our main question, how can we compute a polycube labeling directly on the input mesh? The first thing you may want to try is to assign to each face a labeling corresponding to its closest principal axis. And sure, that works pretty well. It might even be correct for some simple shapes, but in many regions this produces enclaved patches, so that's not really a satisfying solution. To improve on this simple idea, Livesey and colleagues proposed to incorporate it into GraphCut, which allows us to penalize boundaries and produce simpler labelings. This is an improvement, but there are still many invalid charts, highlighted in yellow here. So how can we measure labeling quality? Let's first try to get a bit of intuition by considering this labeling. See this white patch in the center? It's surrounded by one chart in the back and another blue chart here. And in Polycube space, this blue chart will have a constant value on the vertical axis. meaning that this white chart will collapse. So that's what we call an invalid polycube. We can use this as criteria to evaluate labelings. In that case, the labeling is invalid because the white chart has fewer than 4 neighbors. This can easily be detected by looking at the connectivity of the labeling. Similarly, a labeling with a boundary separating two charts with opposite labels will be considered invalid. And finally, a vertex at the intersection of 4 or more charts will also be considered invalid. A labeling which is free of all these 3 defects will be referred to as pseudo-valid in the following. So while pseudo-validity is necessary, it doesn't mean the labeling is a good fit. Consider these 2 bumpy cubes, for instance. Both are valid, but if you look at their corresponding polycubes, one is a much better match. We need to define a fast method to evaluate this parameterization distortion. So now consider a single triangle being mapped from input space to polycube space. There is a linear transformation f that corresponds to this mapping, and we would like to penalize f for stretch but not for rigid transformation. This can easily be measured with the Jacobian of f and specifically with the singular values of the Jacobian. From there, we define a workability energy that measures the amount of polycube distortion. And now that we have this metric, we can try to minimize it using a heuristic. In particular, a genetic heuristic seems especially relevant to our problem at hand. So here's a quick recap of how they work. Starting from an initial solution, generate a range of different solutions with mutations. Some will be beneficial and some detrimental, illustrated here in red and in green. Then combine pairs of them randomly using a crossover operation. This will produce even worse and even better solutions. But what matters is that some solutions will be lucky and combine both good mutations from both of their parents. Finally, you need to discriminate between good and bad solutions with a fitness operator that discards the bad solutions, and the good solutions are inserted back at the beginning of the algorithm. Then you repeat this process for a number of generations, and at the end you output the best solution that was produced. So in our case, if we think of our labeling as a vector of per-phase labels, then we almost have a full genetic algorithm. We're only missing mutations and crossover. So starting from this initial solution, let's define a genetic framework. Mutations first. Here we can implement any operation that modifies the labeling. Of course, modifying triangles at random without considering the labeling's topology would almost never be beneficial. Instead, we implement 3 operations that have a fairer chance of improving the labeling, but not always, and that's fine because the genetic algorithm will discard bad solutions anyway. So first, we split the chart by adding a pass following one of the principal x's. Second, we remove a chart and replace it with its neighbors. And third, we propagate the chart along its boundary. And for crossover, we also cannot naively merge the 2 vectors, because that would mix charts in regions where the parents disagree. We want to define a crossover such that if both parents have beneficial mutations, then both are present in their offspring. So instead, for a given triangle, we pick the common label when both labelings agree, and if they disagree, we pick the label that was changed in the most recent generation. Finally, at the end of every generation, we insert every new solution back into an archive. The archive is ordered by fitness and it has a limited size, so in order to be accepted into the archive, a solution must have a better fitness than the worst element in the archive, and then it takes its place. So that's it, we've defined a genetic framework for Polycube-Maps. Now let's have a look at some results. So as explained in the beginning, we incorporate our Polycube method into a hex meshing pipeline to evaluate it. So we can measure its success at different steps. First, we check whether our method finds a pseudo-valid labeling. Second, looking at the Polycube, we measure its area distortion. And finally, we measure the quality of hex meshes with the minimum scale Jacobian. So here, dark blue is a perfect cube and yellow is a very low quality hex. We evaluate our method on a dataset of over 1,300 models that includes both CAD and natural shapes. Evocube generates pseudo-valid labelings for the vast majority of inputs. It also succeeds in generating polycubes with low area distortion in a much wider range of cases than previous works. And the resulting hex meshes are also satisfying in the overwhelming majority of cases. By virtue of its genetic nature, our method is highly parallelizable and computed labelings for our complete dataset in around 5 hours. In this dataset, Evocube succeeded in finding valid polycubes for some very challenging shapes. If we look at this model, for instance, it managed to separate this blue chart and that blue chart by adding a red chart in between, which in Polycube space corresponds to this step. And in practice, this means that this chart can be higher than this chart. Which in the final hex mesh will mean that there are more hexes vertically here than there, which makes sense obviously since this part is taller. On this one, a path is added across the top so that this wedge here on the right doesn't collapse in Polycube space, and you can see that it is meshed appropriately thanks to this labeling. Now let's compare our meshes against an octree-based method. So the good thing about octree-based methods, like I said in the beginning, is that they're very robust and they're able to adapt their resolution locally so that they can mesh anything. But it leads to very poor meshes. In comparison, you can see here that the meshes produced by our method have many qualities that they lack. They have better scaled Jacobian, the hexes in our mesh are nicely aligned with the features, and also all hexes are approximately the same size. And all these properties are very appreciated for finite element simulation. But let's also look at some of the shapes that we failed to generate labelings for. So the first one here is very poorly aligned with the principal axis. You can see this box is oriented 45 degrees, and then inside of it, it has rods which are themselves oriented 45 degrees from the horizontal plane. So these shapes tend to be very hard to turn into polycubes simply because their features are just not aligned at all with principal axis that polycubes rely on. The second is a very complex shape with a very intricate topology. And the third one simply has too low of a meshing resolution for the holes to be labeled properly. So this happened a couple of times in the dataset. That's just, the resolution is just so low that there's no labeling that can properly label this gap, this hole, for instance, since it has only 3 sides and you would need a labeling with at least 4 labels. Finally, I just wanted to say all the hex meshes presented in our paper can also be viewed directly online on hexalab.net. There's no download or anything, you just open it in your browser and select Evocube, so feel free to check them out. To sum up quickly, in this presentation we have described a method to compute Polycube labelings. We proposed a novel genetic framework that generates a great number of solutions and combines the most promising ones, consistently producing valid polycubes across the vast majority of inputs. So yes, that's it. Thank you for your attention.